name is Katharine Cannatella, and this is my Lab 9 video lab, The Physics of Extreme Sports with Ropes. The objective of the problem was to model the motion of a spring mass system using the momentum and energy principles, then compare the results to the experimental data. The results were that the model is a successful prediction of the motion and satisfies the energy principle. This is the video on tracker of the spring mass system. The equilibrium length was 0.7 meters, which is what I set my calibration stick to. And I chose the origin of my axis at the fixed attachment point and had the spring located in the negative y direction. From here I obtained my x and y values for the spring mass system. I'm now going to run the video. This is the code that I used to run the simulation. The mass of the ball was 0.402. The initial position, as shown on tracker, was negative 0.104 and negative 0.656 and 0. I then loaded the data from tracker to compare it to the model. There's the gravitational constant and spring constant, which I got from the period of the graph on tracker. Ks equals the mass times 2 pi over t squared, and I found the value for Ks to be 6.8691. I then found L naught by using Fnet equals Fs plus Fg equals 0. I rearranged the equation, finding that L naught equals negative mg divided by the spring constant plus L, with L equaling 0.7. I then found L naught to be 0.1264. The video lasted 9.212 seconds. I used the momentum principle to update the position of the mass. Because I am limited with time, you can pause here to look at my calculations. Further down in the code, you can see that I updated the changes in energy of the system. The system is the Earth, the mass, and the spring, so delta E is equal to delta UG plus delta KE plus delta US, which equals the work done. I'm now going to run the module. The plot will show the mass's movement in the y direction. The orange ball shows the model, while the blue ball shows the experiment. In the plot, the red line shows the model, while the green line shows the experiment. You can see that there is pretty good agreement between the two. For the first what does it mean question, I had to compare the period of oscillation I found from examining the x component of the position with the period of oscillation determined with the y component of position. Do they differ? If they differ, can you explain why? In the x direction, the model and the experiment were in good agreement. However, they were a little bit more off than the y oscillations. This is because the periods of oscillation between the y and x direction are different. This can be explained because in the x direction, the movement acts more like a pendulum than like a spring. Pendulums rely on different factors than springs, and that is why there is less agreement. The second what does it mean question says, with your choice of system, determine the work done by the surroundings. Is the energy principle satisfied? Justify your answer. I also plotted the change in E as represented by the red line. As you can see, it is 0, which means the work is also 0, because delta E equals work. Therefore, you can see that it follows the energy principle because I chose my system as the mass, earth, and the spring. The third what does it mean question asked if I shifted the origin, would it change the physics of the system? If I changed the origin, I would change the spring position and the ball position. Therefore, the spring constant and L naught would be the same. All the oscillations on the graph would then be shifted and the period would be the same. Because all these values would remain the same, it would not affect the physics of the system.